right, good morning, everybody. Today is the second episode of the virtual sessions from the RPA. Today's webinar series is featuring Jay Egg from Egg Geo. This little QR code here will bring you to our YouTube page with the Radiant Professionals Alliance. We have our own channel here. We'll be preparing all sorts of educational content and webinars free of cost, available to the public for everybody to check out, save for later, like and subscribe, please. If you can check out that link, we're going to continue to add more and more as we go forward. This is a short webinar series that we started a few months back, and this is in anticipation of our AHR Live at AHR coming up in 2025. So we can ask you to take a look, follow our page, and share it around, please. Just a few upcoming meetings I wanted to share with you guys. Anybody interested in joining the RPA? We do meet twice a year in person. We have two upcoming in-person meetings this year. One is going to be at the IATMO annual conference in September from the 22nd to the 26th at Planet Hollywood in Las Vegas. We're going to have in-person meetings there. We'll have our committee meetings and a whole bunch of really great opportunities to share and network with our teams. We'll be at AHR this year as well. The AHR Expo is shared with the ASHRAE Winter Conference, and we're excited to be there again this year. We'll have plenty of speakers. We will have a couple panel sessions that we plan to put on for all of you guys, and they will also be recorded. We will be doing our second annual live from AHR. I'm excited to share all that with you guys again. And again, this webinar series is in anticipation of leading up to that event. And we're just excited to get everybody involved in what it is we're doing and share with what we're doing. And hopefully you'll join us on the floor at AHR and the IATMO conference, and we'll get to talk a little bit more. So if you guys are interested in speaking for us at any of those events, you can click that little QR code right there, scan it with your phone, bring you right to a Google form, and you can just provide your information, your abstract, or anything you'd like to share with the crowd. So we'd be happy to have you and put you on. Just some general housekeeping. So by the nature of trade associations like the RPA and HIAC, bringing together competitors, which means they're subject to higher scrutiny for anti-competitive issues. Antitrust laws prohibit agreements or coordination of efforts that unreasonably interfere with free and open competition, and penalties for violations can be severe. IATMO and all of its subsidiaries adhere to antitrust laws and expect all webinars participants to do the same. So during this webinar and any interactions outside of it, discussions and agreements that could retain competition are strictly prohibited. This includes exchanging information on individual prices, rates, and coverages, market practices, claim settlements, and practices, or any of the competitive aspects of an individual company operation. So each participant is obligated to speak up immediately if the discussion strays outside these bounds. Your continued acceptance and participation in this webinar signifies your acknowledgement and acceptance of this policy. So the session will be recorded and it will be available for a later time on our YouTube page. All attendees' mics will be muted for the remainder of the session, and please utilize the chat for Q&A, and our speaker will be notified if time permits. So today's session is Jay Egg, the future of heating and cooling using thermal energy networks. So we're thrilled to have Jay here. He's a true leader in the clean energy industry. As a founder of Egg Geo, Jay has revolutionized how we think about geothermal and thermal energy networks. Jay isn't just a thought leader, he's a builder. He's an influential role in the Radiant Professionals Alliance, where his insights and advocacy are driving forward the adoptions of this game-changing technology. Additionally, Jay's contribution to the IATMO Uniform Code committees are helpful in setting standards for a more sustainable future. So today, Jay's here to share his expertise and vision for the future of thermal energy networks. Whether you're new to geothermal or seasoned professional, you're going to leave with some valuable insights that can certainly transform your idea of what it means for decarbonization. So without further ado, I'd like to bring on Jay Egg. I'm going to stop sharing my screen and allow Jay to share in. Thanks, Jay.
Thank you, John. I always love coming on, especially to IATMO-sponsored programs like this. I'm going to share my screen, and we're going to talk about exactly what you said, thermal energy networks. Many on or viewing this as a recorded event may have heard about thermal energy networks. But I like to start from scratch each time because we're constantly getting new folks involved with it. So as I start from scratch, I love to share this image. It's an image actually from 2014, so it's 10 years old now. And it came about because in our work with the New York State Energy Research and Development Authority, NYSERDA, we were asked by the City Council how it could possibly happen that they could get 900,000 out of their 1.1 million buildings on geothermal exchange for the purpose of providing energy exchange for the heat pumps that would be required to decarbonize and electrify New York City and New York State. And we explained that you got to get out of the mindset of thinking that you only drill one borehole for each ton or for each building, or a multitude of boreholes for each building. Instead, there's something called load diversity, and there's energy sharing between buildings. And so we created this image to kind of show them how, and we explained that in the middle of the winter time, even on the coldest day of the winter, your office buildings and commercial facilities, such as manufacturing facilities and so forth, would be cooling dominant. When a building is cooling dominant, it means it's producing heat that has normally exhausted the atmosphere year round. And at the very same time as that's happening in the middle of the winter, there are apartment buildings and single family homes and other heating dominant buildings that need that energy. The way to, and it's the same thing that universities have done for decades and other campus-based facilities. They've been able to reject energy to a common or an ambient loop, and that energy can follow a pipe that's filled with water and carrying BTUs, and the rejected energy from cooling dominant buildings can be absorbed by the heat pumps in heating dominant buildings. And so what we basically were able to prove out to the New York City Council and to NYSERDA and to anybody that would listen, because we did the first of these back in about 1990 ourselves in Florida, is that you can decarbonize buildings simply by using the waste heat that's already in your built environment. So in addition to the fact that you can harvest energy from cooling dominant buildings, you can also harvest energy year round from surface water, from wastewater, and you can build these buildings in a smarter way where sometimes you need energy piles, or structural piles for the building, and you can turn those into energy exchange piles. In addition to that, you can, there may be combined heat and power plants that can be turned into exchange facilities. And it goes on and on. If you happen to have subways, you can extract and reject energy to that. So what I'm going to do is I'm going to share a little bit, because things are constantly changing in the industry. And I'm going to share just a little bit about where I was last week. I got to take a trip last week at the invitation of the United Association of Plumbing and Heating Mechanical Officials, basically the industry trade group for our pipe fitters and plumbers. And I got to take, here it is right here, the United Association of Union Plumbers, Fitters, and Welders and Service Techs, to Ann Arbor, Michigan. And they've been having an annual training symposium there every year for decades. And while I was there, I got to spend some time, as usual, listening to what's the latest and greatest. And by the way, right now, they're sitting at almost 390,000 union workers in the United States. And so what that creates is a real opportunity for our industry to say, we're building this massive plant, and we need 2,000 pipe fitters on the job next year at this time. So they can plan for that, and these union pipe fitters and plumbers can be there. And so at this is such an important trade group that during this meeting last week, this is Rob Vilches, the training director for the UA. He gave Secretary Granholm, the U.S. Energy Secretary, a tour around the facility. And this is the link to the actual news report where you can actually see them going through. And behind Secretary Granholm here is the president of the UA, Mark McManus. And so this is just an idea of how important thermal energy networks are to the United States, because a lot of what the UA is focusing on is thermal energy networks. And I'll explain to you how we know this. In New York, in 2022, the UA recognized thermal energy networks as the decarbonization strategy that could put a lot of pipe fitters to work, because you just saw it on the last slide. There's a lot of pipes that are going to be going into the ground. So they made that the UA got behind this effort in New York, and New York in 2022 unanimously passed the Utility Thermal Energy Networks and Jobs Act of 2022, which monetized thermal energy for the utilities. In other words, electric utilities and gas utilities can now sell thermal energy that's waste heat from one building to another. We're going to talk a little bit more about that. But going back to the really cool event last week that went all week long, you can go through and see displays of folks saddle tapping Aquatherm pipe. We got to have a great little dinner there where Mark McManus and Jennifer Granholm had a sit-down talk. Secretary Granholm addressed the apprentices for quite a while. They had a lot of their trailers out in the back 40 that they travel around the country, displaying some of the latest technologies. Here you can see orbital welding going on. And just to let you know how important this is, the UA is currently commissioned the creation of thermal energy network trailers so that they can train folks on how to, their apprentices on how thermal energy networks work and how they're going to be installed underground, which basically it's like installing a whole new potable water system underground, because that's how we're moving the energy. So, and this is the inside of a couple more trailers. You can see some air handlers and some fire piping and so forth. They have the best training apparatus in the industry right now. I'm going to move from that. I am going to get really focused here in the last 45 or 50 minutes on the basics of thermal energy networks, but I like to do some of the bragging things at the beginning. There is a new report out from the Building Decarbonization Coalition. It came out like 2 weeks ago. This is a phenomenal report. It talks about water smart buildings. And once again, as a follow-up, if you ask John for it, he can send you, because I'm going to send him a copy of this presentation when I'm done, and he can send anybody that asks a copy of it, and you can grab some of these hyperlinks here if you're not able to look it up right now. But what this did is it talked about, and if you can't see it here, it's showing a thermal distribution loop in the street here, and what it's showing is cooling towers being removed from buildings. And the purpose of the report is to show something that people don't really think about. When you put in a thermal energy network, you're by definition eliminating a lot of the cooling towers, if not all the cooling towers off the buildings. You saw it in the first slide. Well, what you might not be thinking about is cooling towers use a lot of potable water, because that's called an adiabatic cooling process. And what is required for that is potable water, which is put into the cooling tower and is evaporated, a great portion of it, and the remaining portion is blown down to blow out impurities that become concentrated in the water. So thermal energy networks can save billions of gallons of potable water every day, quite honestly, every day in the built environment. If you look at this is from the report, it shows that basically what it's showing here, and I'll just interpolate it for you, is cooling towers are the number 2 consumer of potable water in the built environment, even more than irrigation in the built environment, but just less than restrooms and kitchens and so forth. So kitchens and restrooms use the most, cooling towers use the second most, irrigation is down from there. You can see in office buildings, the percentage of water for temperature control is right up here, approaching a third of the consumption. In laboratories, it's even more. Hospitals, quite high, hotels, and so forth. This happens to be the geothermal energy network going into Framingham, Massachusetts, the first of the new breed of thermal energy networks that has come into play. Is put in by Eversource up in Massachusetts. Just for a scope, this is another, and this is the link to the report here, which we'll be able to share. I would link to this, but we wouldn't have time to do everything I want to do today. So we're just going to save this. You can look at it later. But Ball State University, one university, annual water savings, 45 million gallons. Colorado Mesa University, another university, 10 million gallons. Cornell University, Ithaca, New York uses the lake source cooling system instead of cooling towers, 4 million gallons. Enwave Energy Corp, Toronto, Canada, saves 220 million gallons of potable water a year by using geothermal exchange. Phenomenal. Now, I want to tell you something because I won't have a chance to say this later. In water stressed areas such as California, Nevada, Arizona, even Utah, Florida, Texas, did you know, because we've done these studies, where 30 years ago electricity was the number one ROI factor in a geothermal system? Not so anymore. Water savings is the number one factor in payback in a geothermal heat pump or geothermal source chiller system. Why? Because water costs have gone up so much over the last 30 years. So when we do an ROI, for example, in Florida, which is where our main offices are, the number one resource for payback is water savings in actual dollars in cost. The number two is electricity. So it is becoming a major factor. And in addition to that, it just makes good sense. All right, now we're going to get into the presentation. I just want, like I said, I like to start at the very beginning. So we're talking about geothermal heat pumps, which are the integral part of tying into a thermal energy network, because a thermal energy network, we're going to talk a little more about it, is the movement of energy through a city using water pipes, essentially. In the two types of systems that we can compare with regard to heat pumps, which are an electrification and decarbonization strategy, air source heat pumps, as you can see here in the wintertime, they use an outside condenser that is able to pull heat out of the cold outdoor air, concentrate it through the Carnot refrigeration cycle, and discharge that heat into the space, providing the heating you need to keep yourself warm in the winter. The way a geothermal heat pump does it is, instead of pulling it from below freezing conditions outside, it is able to pull heat from the subterranean earth. And that temperature is going to average somewhere between 45 and 75 degrees, where depending on where you are in the continental United States. Either way, listen to what I said, 45 to 75 degrees beats sub-freezing temperatures in the winter and 100 plus degrees temperatures in the summer. I live in Phoenix now, and we have had the longest run of 100 plus degree days since 1993. And I'm sure a lot of other cities in the United States can say they've experienced record heat, as also probably in the winter they're experiencing record cold temperatures. So at any rate, the real benefit of geothermal heating and cooling systems lies in the fact that you have a more stable heating source for wintertime and a more stable heat rejection opportunity for wintertime. So as we move forward, you can kind of see, I like to make it simple. Everybody knows the brand Carrier. Carrier makes both air source heat pumps and geothermal heat pumps, as does every major manufacturer of heat pumps. So they are not any different in concept, except that one has an outside condenser that is moving air over those coils so that you can cool and heat depending on the season. The indoor variety, or the geothermal heat pump, is the same technology. It's just that the compressor is now in the bottom section of the heat pump right here. There's actually the same compressor as you would have outside in the bottom of the heat pump here. And instead of an outside air coil, it's using what's called a coaxial water to refrigerant coil in here. And it's pulling, and this closed loop fluid loop here is exchanging heat with the ground through that coaxial coil. And so that's how it does all of its heating and cooling. So instead of having an outside condenser, it has an outside geothermal coil that goes underground. So when you see a geothermal heat pump, there's nothing to see. That's the interesting thing about it. It's the only renewable technology. If you think about solar and wind, you've always got something to see. Not with a geothermal heat pump. When a geothermal heat pump's in, there's nothing to see. It's all hidden. And so geothermal systems are kind of like the quiet technology. There's a lot going on when a heat pump goes in because they've got a trench and they've got a bore and they've got to do all this other stuff. But when it's done, just like in this Washington, D.C. home, this is all you see when you're done. If you walked around this guy's house, you would not see anything outside. So what's not there, it kind of becomes anticlimactic because you don't know what you're missing because you don't even think to look for a heat pump. So that's the interesting thing about geothermal systems. And that missing component is also a huge benefit because there's nothing to see, there's nothing to waste away. I want to point out that this technology, for any lay people out there, it's the same technology you have in a home refrigerator. It has a Carnot refrigeration cycle, and in order to get that box from 75 degrees room temperature down to 40 degrees and that freezer down to -5, it uses that compression cycle to pump that heat out onto the floor where you feel it at night when you go to get that snack on your bare feet. That's the same way an air conditioner is working. It's pumping heat out of the indoor space through into the outdoor space using an outdoor condenser. So looking at these two systems here, you can kind of see that this is the ground loop, this is the refrigeration loop, and this is the home loop. And you can distribute this either radiantly in the floors, using radiators in the walls, or using forced air like you see here. Also indicated is a domestic hot water tank, because guess what? You can very easily get a domestic hot water loop with your geothermal heat pump. You can also buy a pool heat pump that can tie into the same loop and provide all the heating or cooling you need for a pool. Interestingly enough, if you get below the Mason-Dixon line, you often need to cool pools in the summertime. So forced air and hydronic distribution are two different ways to distribute energy. And by the way, hydronic distribution is always the more energy efficient way to do it. A quick primer on how we rate and how we measure heat. Heat is measured in British thermal units. A British thermal unit happens to be the same amount of energy as you would get from striking a wooden matchstick and burning it from top to bottom. 1 BTU is also the same amount of energy that is required to heat 1 pound of water 1 degree Fahrenheit. So coefficient of performance is the measurement in BTUs delivered divided by the BTUs consumed. Interestingly enough, air conditioners are often rated in EER, which is a different way of saying the same thing, but it mixes units. EER is the net cooling capacity divided by the applied energy in watts. And a quick conversion is EER equals COP times 3.412. And the conversion for that is very simple. 1 watt of electricity equals 3.412 BTUs. In other words, if you apply 1 watt of energy to 1 pound of water, it would raise it 3.4 degrees Fahrenheit. So understanding that, let's look at why heat pumps are all the rage. If you're heating, we understand that we're trying to decarbonize the built environment because, as we understand, CO2 emissions are contributing to to global warming. So we're trying to stop combustion of fossil fuels for the purpose of heating buildings. So if we go all electric, you'll see that you can use a space heater, which 1 kilowatt of electricity going into a space heater is going to deliver. That's why I gave you the conversion formula back here. 1 watt of electricity equals 3.412 BTUs. So 1 kilowatt of electricity going into a space heater is going to give you 3,412 BTUs per hour of heat. If you put 1 kilowatt, that same kilowatt of energy into a heat pump is exactly that. It's a pump. It is not using that electricity to burn to make heat. Rather, it's using that electricity to run a heat pump. So a heat pump is doing what a heat pump is supposed to do. It's pumping heat out of the ground in this case. So for 1 kilowatt of electricity, we can pump 4 units of heat out of the ground for a grand total of 17,000 BTUs per hour of heat. So that is 5 times the amount of heat you can get from an electric resistance heater, which plays into what we're going to talk about in the next slides. And we'll get to that in just a minute. So using these heat pumps, and there are as many different types of geothermal heat pumps as your imagination can come up with. These are, for example, the stackable units you might see in Marriott hotels or in office buildings. These are terminal air conditioners like you might see in Days Inns or your 3-star hotels. These are horizontal heat pumps that might go between the floors in office buildings or above the ceiling in a home. This is a commercial heat pump here you might see doing an auditorium or a common area, as you see here. This is a dedicated domestic hot water heat pump that does nothing but provide potable hot water. This is a dedicated pool heat pump. These heat pumps use different terminologies. If they use water source, in other words, tied to a geothermal system for distributing forced air, it's called a water to air heat pump. If it uses water to go to a water production, such as in domestic hot water or pool heating, it's called a water to water heat pump. And then there's vertical orientation, horizontal orientation, and all kinds of other things. As a matter of fact, as we begin to convert our built environment to geothermal heat pumps, you can get any type of geothermal heat pump you might imagine. For example, on top of Home Depots and other big box stores like Walmarts and so forth, there are geothermal heat pumps you can pop onto existing curbs, and you can replace the gas lines that go to those gas packs with geothermal lines on top of the roof. There are 100% fresh air geothermal heat pumps that you can install in this built environment. And now we start to get a little bit more into tying this all into a district thermal energy network application. This is very similar to the first slide I was sharing with you, where you look at the commercial office buildings, the factories. If you look at these little red arrows, they're indicating these are cooling dominant buildings. Even in the middle of the winter, they have so much in the way of internal gains from data processing, computers, and manufacturing processes or people. They're constantly emitting heat. And when you tie these in to a thermal energy network, then your residential users and your mixed use clients and built environment type folks can use that heat, and it can go straight into the heat pump. And what it does is takes what is already in a very efficient heat pump. As I shared earlier, it might be operating at a 5.0 COP, which means 1 kilowatt of energy is going to give you 5 kilowatts worth of heat. Well, did you know, and this is a fact that I'm sharing with you, because of this diversity of load, meaning the waste heat from one building is the consumed heat in another building. When it's operating in that fashion, you can end up with a COP, a system COP of 9 or 10. That is unbelievable. That's practically, it's approaching what we would call perpetual energy production. We know that's impossible. You can't have that. But when you're sharing energy between buildings, especially in the dead of the winter, you're approaching such a load diversity that it is impossible in any other scenario except in a thermal energy network or a shared network of some sort. So this is where I like to pause and talk about, we've already talked about, okay, thermal energy networks can use waste heat for sharing between processes and other buildings. But here are some of the other things that geothermal or thermal energy network communities can boast that you can't get out of air source heat pump communities. There is no more outdoor equipment to replace, which is a huge benefit. Uh, Coming from Florida, when we did coastal applications, whether it was commercial or residential, those applications, even with Seacoast coated coils, were lucky to last 7 to 10 years. In a geothermal heat pump application, you're going to get 27 years on average out of a heat pump. Why? Because it's all indoors. There's nothing to weather away. And even in the kindest environments, you're lucky to get 15 to 17 years out of an air source heat pump, where, like I said, you can get 27 years. They're more hurricane and storm resilient. If you don't have outside condensers on top of buildings and sitting outside of buildings, they're not going to get blown away or damaged by hurricane or storm situations. HVAC longevity, we already talked about. No combustion boilers, no cooling towers or furnaces, which plays into decarbonization and plays into savings for precious water. This noticeably superior comfort in heating and cooling modes is something that you understand very easily if you understand how hard it is for a heat pump to heat when it's very cold outside or to cool down when it's very hot outside. Heat pumps, by definition, are going to give you more comfortable indoor conditions when the average temperature or the temperature of the source and sink is a more average temperature. It's just going to give you a much superior comfort in heating and cooling modes. And this is something you have to experience. I haven't seen a lot of reports on that coming out of the DOE or anything, but it's something that's commented on very commonly by people who use geothermal systems. It is just such a comfortable heating environment and cooling environment, both ways. You get this remarkable system efficiency at a standard equipment pricing. This equipment, like I said at the very beginning, is the same technology as air source heat pump equipment. So if you buy a builder grade air source heat pump, there is a builder grade geothermal heat pump that's going to cost about the same. So don't think of these heat pumps as something that's premium and expensive. It doesn't have to be. It's the same animal. And thermal energy networks are infrastructure that is permanent. Just like, I like to use this example. If you were the first person to put in indoor plumbing, you first had to do, if you didn't have it, you had to put in a well, which at today's prices, a water well is going to be $20,000, and a septic tank that's going to be another $20,000. So to put in that very first kitchen sink, it's a $40,000 investment. But once you do that, you can do all the fixtures in your home. The same thing is true with a geothermal system, or you think about it as a city water main or a city sewer. Yeah, it's very expensive, but once you put in the infrastructure, adding on is not that big of a deal. And it's the same thing. Once you put in the infrastructure, and that's what the federal government is monetizing right now, it is done. And by the way, they're monetizing it. In case you don't know, because I don't cover it a lot in this, the IRA is very much focused on thermal energy networks. You can get up to 50% of the entire, even if it's a $500 million thermal energy network for a city downtown district, the federal government will monetize that at 40 or 50%. That is if you use union labor. The federal government's very very high on unions because they want to keep people at a living wage. I like to compare these two systems like by doing this. In case you don't know, in the 50s and 60s, in the 1950, there were no natural gas networks. If you wanted to heat your home, you either did it with wood or propane or something like that. Then natural gas became very abundant. We had just finished our first transcontinental pipeline that we had to build during World War II from Texas to New York so that they could get the oil from Texas to New York without the doggone ships being sunk off of the east coast of the United States. That's why they did it, because the ships couldn't make it around without the U-boats sinking our ships. So we did this big transcontinental pipeline. Well, we took that technology, and natural gas became very hot during that time. And so we put in during the 50s and 60s 2.5 million miles of natural gas pipeline in our cities, connected to 60 million buildings. We did that in the 50s and 60s. So I want to point that out because we have that network presently. I live in Phoenix and I have natural gas coming to my home. You want to know my natural gas bill? I rent a home here. My natural gas bill is $22 a month. How does that pay for any infrastructure? Yet the utility put it in. So natural gas, which is infrastructure, is a pipe in the ground, is consumed. A thermal energy network, which is geothermal, is done by earth exchange. It's still the same infrastructure. It's distributed the same way, except the pipe in the ground that goes to a furnace or a boiler in a natural gas network and provides heating only. In a geothermal or a thermal energy network, it goes to a heat pump, which provides 300% plus efficiency and provides heating and cooling. The reason I put this together, and this Venn diagram came from actually Ontario, from a good friend of mine, Dave Hatherton, the founder of Water Furnace. This basically shows that we're doing today what was done during the 50s and 60s. It's no more monumental a task than we did in the 50s and 60s. And it provides both heating and cooling and domestic hot water now. S&P Global Market Intelligence said of thermal energy networks that these are the last great frontier of energy distribution. As a matter of fact here is that 50% of the energy used in our built environment could be satisfied with thermal energy exchange. And that means we're wasting a lot of electricity and combustion on what can be satisfied with thermal energy exchange. And so that is one of the things that we're working on right here. As a matter of fact, this is just anecdotal, but back before natural gas was a really big thing, the National Electric Manufacturers Association was promoting all electric buildings rather than wood burning and propane burning buildings. They were saying this is a much safer way to do it. And they even put out these gold medallions that gave these homes this total electric award. And we're headed that way again, not to these medallions, but something similar. Now, you might wonder, as a lot of people do, okay, we're going to put all of our built environment on all electric now. What is that going to do to the electric grid? And this is a very important slide to show that, because in the ASHRAE building in Atlanta, at the Atlanta headquarters, in 2010, they did the entire first floor with air source heat pumps and the entire second floor with geothermal heat pumps. And they said, how does the load profile look electrically? And I want you to look at the peak electrical demand of the air source and geothermal heat pumps in the middle of the summer here. Okay, it's obvious, like we talked about before, that the air source heat pumps are going to struggle a bit when it gets below freezing in the wintertime. And that's okay. Air source heat pumps are great, but they just can't keep up with the fact that the ground stays warm all year round. So what do you see happening? This is the point. The air source heat pumps go up And that's why everybody's screaming about what is this going to do to our electric grid profile nationally, while the DOE notices this. The geothermal heat pumps, which peak out here just below the air source heat pumps, have an even lower peak in the wintertime. So what does that mean? All the screaming about what electrification of our buildings is going to do, if we do it with thermal energy networks, guess what? The current snapshot of electrical demand in the United States presently can be more than satisfied when we go to thermal energy networks because it's a lower demand in the wintertime. And yes, this even counts all the way to Ontario and Canada. We have a lower demand for heat pumps in the wintertime than even in the summertime if we go with thermal energy networks. That's why so much is being invented and incentivized at the federal and local levels. And it's shown over and over again. This is the tale of two buildings in Oklahoma, two office buildings, identical. One used air source heat pumps, one used geothermal heat pumps. Summertime, this is July, you can see how close they get. Wintertime, not even close. So Ontario did a study on this, exactly like what we're talking about. Ontario did a study that was commissioned by HRAI and performed by Dunsky, a very reputable government study agency. And they said, what if we converted, how much would it cost to convert the entire province of Ontario, which is about 7 or 9 million people, somewhere in there, to air source heat pumps? What if we did it all to geothermal heat pumps? So they have air source in this darker purple or blue here, and this teal is the hypothetical geothermal heat pumps. So immediately they say if we convert everybody to geothermal, we're going to save $1.1 trillion in natural gas. That's the immediate thing. And the investment is going to be $137 billion more for geothermal heat pumps. Why? We got to put in the ground loops. Okay, simple. How much are they going to save? Happened to be 137 billion. There's your payback. But that doesn't show the whole picture. This is how much they're going to save in electrical infrastructure. The power generation required upgrades required for air source heat pumps would be more than $1 trillion. They would save $494 billion in electrical infrastructure upgrades going with geothermal heat pumps. Exactly what we were just talking about. It saves on electrical infrastructure by doing that. In addition to that, I love air source heat pumps as much as the next guy. When they're brand new, they look beautiful. When you're in an urban environment, they can get pretty messy pretty fast. And I've serviced a lot of wonky things. By the way, I'm a tradesman. I'm a tradesman turned white collar over the last 14 or 15 years. Back in 2010, I was still carrying my tool belt up a ladder like this and going, who the heck permitted and approved this? And I doubt this was approved by, because I don't know. But the point is, this is what happens. We know this is what happens. Even when it doesn't meet code, so many things fly under the wire and get approved that we don't agree. This is the fact of the matter. And really, it gets, homeowners end up doing this because they're considered appliances and so forth. It becomes a nightmare that we have to deal with as tradesmen. That's where IAPMO and RPA and everybody else that regulates this industry. And hats off again to John Mullen, because he is such a champion for the industry, such a champion. I get to serve with John. I'm on the International Association of Plumbing and Mechanical Officials, UMC committee. And guess what? In 2015, we got geothermal under the tutelage of Lance McNevin, who was the chair, into the Uniform Solar Hydronics and Geothermal Code. And in 2021, we got it into the UMC. In 2024, it even went further, and now we have thermal energy networks language coming in for the 2027 code. In addition to that, CSA 448 has thermal energy networks language coming in. We are kicking some booty on this. And why? Because this is what's happening. whether you know it or not, thermal energy networks are happening nationwide. We're personally on. I was just told one of the projects we're involved in Salt Lake City is the largest infrastructure project ever undertaken by Utah. I did not know that till somebody told me that over the weekend. We've been working on that with Utah for some time. In addition to that, we have the privilege, and we continue to have the privilege of writing we have the tremendous privilege of writing textbooks on this technology. These are some McGraw-Hill textbooks we've written. We've written a lot of kids books about this. You can go on to our website and you can download free activity books. You can download free kids coloring books and everything. In addition to that, across the pond from Norway, they published Our Hidden Powers, which is all about geothermal. It's a really cool book. It's for sale, but we're an advocate of this because it's just a great little geothermal book. In addition to that, we're working with government agencies throughout the country, including NYSERDA, including SUNY, providing training for their professionals and employees. We're working with state agencies and cities across the United States. This is Rochester, Minnesota, where it's showing a drill rig here. We've been working with them since July of last year on a major thermal energy network and that happens to be the city where the Mayo Clinic is. And Mayo Clinic is doing a $5.5 billion expansion right now. This is where we center our efforts with the UA, with IAPMO, with RPA, with the Hydronics Industry Alliance. We partner a lot with PHCP Pros because they publish good information on this technology constantly. We write, one of our employees, Mimi Egg, is a commissioned writer for PHCP right now, and she provides a lot of great younger perspective on these things. So these systems are going in rapid fire. I'm going to kind of go rapid fire through some of these last images because I just like this one right here. This is a bunch of good old trade boys from Tampa where we were putting in. The cool thing about this is it went into a church that had been geothermal since 1949. And in 2013, they had their very first air conditioning upgrade because it operated for 63 years on the same chiller. This is the public safety complex in Pinellas County, Florida. You can see the massive size of the complex and 911 facilities. Why did they choose geothermal? They were able to get rid of their cooling towers, and that made them weatherproof. And of course, they are able to save quite a bit on water, and they're able to get everything underground. Cornell, this is such a magnificent example of how geothermal can be done in more ways than you can imagine. There are at least 7 different major types of geothermal resources for heating and cooling. And under those 7 different ways of tapping into the earth, there are countless variations. And this is just one. In New York, in the city of Ithaca, where Cornell's main campus is, they tie into Cayuga Lake. And Cayuga Lake is their main heat sink for cooling their whole campus. As a matter of fact, it's so cool that they are able to cool their campus most of the year without any active refrigeration. Can you imagine that? How efficient is that? When you're able to chill your campus because the bottom of Cayuga Lake is 40 degrees or below. And they have chillers there because there are certain times of year they need a little bit of a boost. And they just drill deep wells. Now, Ithaca is not known as a place where you would drill deep and get a hot geothermal resource, but they got a DOE grant and they did drill deep. They got to temperatures approaching 200 degrees Fahrenheit or more. And what they're going to do with that is right now they have a combined heat and power plant where they make all their own electricity right now. They're going to slowly wean off of that and slowly start tying into the increasingly green grid because it's getting more and more power from solar and wind. And they're going to slowly begin to decommission their CHP plant. But where are they going to get their heat? Now that they're not getting combined heat and power, it's going to come from here. So they have heat from geothermal and they have cool from geothermal, but two completely different types. Isn't that cool? And that just goes to show you that you just never know. When you think you know everything, you learn something new. This is their campus at Roosevelt Island in the city, and they use standard geothermal here, but not quite standard. I don't have the time to explain exactly why it wasn't quite standard, but they did something really cool here. And you can read about that if you Google the Cornell Roosevelt campus, or you can email me if you want to, and I'll send you a case study on that. So here's the point. When you're creating a thermal energy network, which by now you should understand is the tie-in of multiple buildings in a diversified load where they share energy. Now, when they share energy, what's going to happen? The very best thing is the cooling dominant buildings are going to be able to share energy to those that need heat. But what happens in the middle of the summertime when everybody's exhausting heat? You got to have a really good heat sink. And so that becomes the biggest problem in our built environment now is decarbonization. That means the middle of the winter, all that combustion heating. What it's going to swing to as we do this is we got to get rid of a lot of heat. There's two things we need to consider on that. Where does all the heat go and how do we get it out of here? And I'm going to tell you, number one, we find heat sinks such as surface water, wastewater, closed loop, aquifer-based systems. But what's happening, and I want you to watch this, is there are technologies coming into being right now. They're already viable, but they're not, what do you call it, commercially viable yet. But low-grade heat is now you're able to turn that into electricity. What do I mean by low-grade heat? What's the heat that normally comes out of a chiller when it's rejecting energy? 97, 95. That kind of heat can actually be turned to electricity. It's a very low COP right now, but at least it can be used and turned into electricity. We're going to see more and more of that happening as we have more and more waste heat from these built environments. We're going to be able to turn that into actual electricity. And I'm writing an article on that right now because the viability of that is growing tremendously. I'm going to show you a real case study just for fun. Just real quick, John, there's no burning questions out there that have popped up yet, right? Good, because I'm going to go right up to the top of the hour unless somebody tells me to stop, because I got a couple of exciting things to share. NYSERDA basically asked us when we were beginning to study thermal energy networks. They said, "Hey, we have 2,500 homes here at Penn South in the middle of the city, and they use 5 megawatts of boiler energy to heat these 2,500 homes in the wintertime. How can we heat these buildings without drilling 2,500 boreholes or whatever it is, or 5,000 boreholes?" And we did the study, and we found that across the street here at the U.S. Postal Service, they have an 8 megawatt thermal rejection even in the middle of the winter. We said, if you allow us to study moving that heat of rejection from those cooling towers instead over to the central energy plant here, we can put in a 5 megawatt heat pump that can do all of that. And they said, do it. And so we're on the 6th phase of that study right now, and we'll soon be working on funding this project for Penn South. The engineering is basically done. It is a remarkable project, and that will put our plumbers and pipe fitters to work doing what they do best. Serious infrastructure projects that look like this. This is another one in the Bronx where we're tying in a bunch of schools to a major cooperative complex. This is a NYSERDA diagram showing how all these brown devices, which are cooling towers and outside condensers, are going away. And this infrastructure is going to grow like crazy. This is a study we did for an East Coast city that shows a bunch of different zones like this. This is what it looks like in a line diagram. All of these different quadrants, 9,900 tons, 8,800 tons, 3,600 tons, 4,800 tons, using all of these different sources, wastewater, surface water, aquifer based, are using all these different sources and tying in together to share energy and get everything underground. A pipe fitter's dream, putting our pipe fitters to work. This is from Chicago, where we did our first demonstration to train the trainer for the UA back in 2020 or 21. We basically said, look at the Sears Tower and all these buildings in the middle of January, exhausting heat. All that heat will eventually be piped into your buildings, and that's a lot of pipe fitter jobs. And that is basically my presentation for today. There's our website, UPC, if you want to hear more. Plus, I'll send John this presentation for anybody that wants it. That'll keep him busy if he gets to all your calls. And John, I'm going to call it quits. I'm finished.
Well, thank you so much, Jay. This is a really interesting presentation, as always. I mean, it's fascinating to see all these opportunities that we have around us to sequester this energy from our built environment that we've created ourselves. We've engineered this world ourselves. It's fascinating. Tell plumbers about this stuff all the time. They're really excited about the future of what's to come for utilities and all the like. Ton of work, and we're really excited about it. So again, thank you so much for presenting today, and hopefully people will take this and consider this to be an option for their city, and stakeholders will consider it for their future projects. So again, excited for a nice sustainable future. So we appreciate everything you do for us, and thanks again. Thanks for joining, everybody.
Thank you, everybody.